Welcome, EECS16A. Woo! All right. It's called Lecture 14A, but it's really Lecture -2 in an array, a Python array. -2 is the lecture before the last lecture. Okay? First of all, thank you so much for coming. Really appreciate those who are coming in person. It's always much nicer to teach in front of a crowd, see your faces, and be able to kind of get feedback on, if you're actually getting what we're actually trying to teach. Not that it's as obvious. Unfortunately, Anna couldn't be here today, but she's here in spirit. Okay? So Thursday, don't miss the last lecture. That's Thursday. Can you believe it's the last week? Can you believe it? Can you believe it? Eye contact. Can you believe it? It's the last lecture. Last week. Unbelievable. Wow, we've gone through so much. It's pretty amazing. Okay, so today we're going to talk about least squares applications. And so we can continue the topic. I'm going to focus on you now. We're going to continue the topic that we've covered last time. And last time was before Thanksgiving. So probably you don't remember. Which is fine. Because I'm just going to give you a short overview. But, an announcement. I can't even read my own handwriting. Please read note number 709 on Ed about the lab. There's something about signing up for optional lab in person or optional remotely or something like that. Check it out. Okay, so we had a few trickles signing in, but we would like to have more. So please read that note and act on it. The lab is amazing. The lab is all about acoustic positioning system, which is really what we've been talking about now, about GPS. This is very similar to how GPS works, except that instead of radio waves, you use acoustic waves that travel from speakers to a microphone, and then you want to figure out where the microphone is. So you're going to do trilateration, you do cross-correlation, you do all this good stuff. So it's just everything there, least squares, all implemented beautifully. So it's a great lab. Any questions? Yep. Oh, maybe that one too. So could be. I didn't have a chance to actually look at that. So 709 is about Touch 3D? Yeah. Okay, good. Do that one too. But the other lab, APS also. Don't miss that one. Thanks for reminding me. What else? Anything else? No other questions? Everything is clear? Yeah. Okay. All right, let's move on. Least squares, woohoo! All right. What is least squares? Well, least squares is a situation, if you remember, that we have more equations than unknowns. So it could be a situation where I have AX, A times X equals B, but there is maybe no solution. And the reason that there is no solution is because the combination of the columns of A times X, is the combination of column A. So the range of the columns of A, the range of the matrix, the span of the columns of A, all this good stuff may not be within reach of the vector that we're trying to, reach. So there is no solution for AX equals B. But we want to find the closest solution. And the examples that I gave you was with this lamp. And today I'm just going to give you a different example with this lamp. So let's say the range of my matrix is a two-dimensional space, but I want to reach this thing. So I can't. There's no way. I'm walking in a plane, and I can't reach this. this lamp that I really want to reach. But I want to get close. I want to get close to that lamp. So what is the closest place to the lamp that I can get? The orthogonal projection. And the orthogonal projection, in this particular case, would it be to actually drop a ball from the lamp down? No, it wouldn't. Why? Because it's an angled space. That's right. It's not going to be exactly underneath the lamp because the closest orthogonal projection, because this plane is a little bit tilted, would be a little bit over here. Perfect. But that was the closest, so I got close. I got close to the lamp, and that's what we want. We want to find the closest solution, and this is what we solve when we do least squares. We do orthogonal projection onto the subspace that is spanned by the columns of the matrix A. Okay? So we did that. And we developed and we came up with, oh my God, what did we came up with? We came up with an equation. And we had this beautiful mnemonic for this equation. Atta minus 1. Atta ba! Right? And it's great because now you remember it. Now you remember it. Now you have an equation. And the beautiful thing about what we looked at last time was, we can try to pose a problem. Like, let's say we have, points, and we want to fit some model to these points. And we said, let's do linear regression. What does it mean? Well, linear regression means I need to find two coefficients, A and B, such that it fits the data. We want to find a line that goes through the data, but we can't get perfectly because the data is kind of scattered, and we want to find the best line. How do we do that? Well, we pose a linear set of equations. We put them in A times X equals B. We came up with a right A. We came up with a right B. Now it becomes a least square problem. And we do atta minus 1, atta ba. Or in some cases it was atta. Yeah. Right? So that's just beautiful. This is one of the most useful equations. I mean, seriously. This is super useful. It's no surprise that Anna had it tattooed on her arm. Ask her to show it in office hours. She'll show it to you. Okay, but we also assume that A transpose A is also invertible. And I said that only if A is full rank. If A is not full rank, then A transpose A, and you believe me. I mean, why not? Been a Cal for, 12 years. You just like your first, second year, right? So there's like a hierarchy there. He knows more, maybe something like that. But we're going to prove it today that this is actually the case. Okay, so if A is full rank, then in fact A transpose A invertible. But before that, we're going to talk about other things. Okay, that was kind of like a review. Okay, and the vector B, which is the actual orthogonal projection, is this beautiful symmetry. Look at that. A on one side, A transpose the other side, A transpose in the middle, sandwich with a minus 1. It's just beautiful symmetry. I mean, like it just looks, stare at it. I mean, it's just so nice. Sandwich, A and A transpose, and in the middle is like A transpose A, minus 1. It's like cool. It just came out so lovely. You gotta appreciate math that, just gives you this beautiful expression sometimes that come out. It's like, oh, wow. All right. Okay, so last time we did a few things. We gave some examples. I gave you the case of linear regression. And then I said, what about, how Gauss, was able to find where Ceres is a dwarf planet, where it is. And, basically it was known that planets move in an ellipsoid. And so ellipsoid can be parameterized by a few parameters. Ellipsoid, at least in 2D, it's 1, 2, 3, 4, 5 parameters. And we have measurements and want to find the best ellipsoid that fits the data. And what we did is we said, we have the known position of x1, y1, x2, y2, x3, y3. And then based on this, we realized, wait, this is actually linear. Even though x and y are squared and x times y are also multiplied with each other, they're not the variables. These are just the coordinates that we know. So we fit it into a AP times Y kind of an equation, and turns out that, yeah, all of these are just constants. So we get this matrix A that just pops out. A, B, C, D, E are the unknowns. And then Y turns out to be just 1. And now it's a least square problem. And all we have to do in order to find the parameters A, B, C, D, and E is to do what? Atta! Minus 1. Atta! Yeah. That's it. And we solve it. I mean, think about it. All it takes, like somebody gives you those points, just points. You know that is ellipsoid. You go like, oh, I'll just take those points that I got, and now I'm going to write a function that puts them in a matrix, right? In this particular way, the first coordinate is x1 squared, the second coordinate is y1 squared. And I mean, I know they are, so I write this program in Python, C++, C, your favorite language. Pascal, I don't know if anybody speaks Pascal. No? Basic, I don't know. Pick up your favorite language. You program that, you create this array of matrix. Then you take another array, initialize it to ones, and then you call a function that computes A transpose A minus 1, A transpose times Y, and then you get the result. Super easy. It solves the problem. And now you got the parameters, the best parameters that fit the data in the least square sense. Yep. The what? The error vector B would be all those distances from that square. So it's the error vector, it will be those, this distance, this distance, this distance, this distance, this, from the square pretty much, from that ellipsoid. And then that will be the error vector, because it's really what it is. Sorry, it's A times P minus Y, right? So, actually it's not, it would be probably, minus Y, so it's these coordinates, sorry. So it's this, 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 that will be the error. Okay. All right. Okay. So now let's talk about its differences here. Did we talk about that one? Like exponential stuff? We didn't, right? So here are points. This is kind of like, oh wow, this is March 2020. Remember March 2020? When people thought everybody's going to get COVID, which probably everybody got by now, but or most people, or some people just don't know. Some people just don't know if they got. Then it's just the number of cases grown exponentially, and you got this number, and you want to figure out what is the parameter of this exponent, because that is very useful to, let's say, find rate of infection and stuff like that. Okay, so it's good for information for public health. Okay, so the model is that you have some constant times e to the power of a times x. Now, it doesn't have to be e, it could be like 10, it could be something, but that's another constant, so we'll go into the c. So it doesn't matter. Okay, so it's e, and the e is actually quite an amazing thing. It just comes up in so many places. I love e, natural logarithm, I guess. Or it's just this beautiful constant, 2.71 something. Irrational number. Irrational numbers are crazy. It's like you cannot find two numbers that you divide that actually is that number. Like you cannot find the ratio. It's because it's irrational. It's crazy. By the way, in 16b, you would learn that if you take an irrational number, I'm just going a little bit on a tangent here. You take this irrational number e, you take it to the power of another irrational number, pi. That's another irrational number. You multiply that by an imaginary number, which is the square root of minus 1, or I, okay? So times the square root of -1, which is crazy by itself because it doesn't exist, right? And you know what it equals to? No, -1. All right, that's the beauty about math. But that's 16b, so I'm just going to erase right now and you forget that. Anyway, we have this model. And the question is this a linear fit? Which parameters do you want to fit? Which parameters do we know? We know x, right? Because that's the day, right? X is just the day. Day 0, day 1, day 2, day 3. We know y, that's the number of cases. So we don't know c, and it's in red, right? It's like pretty obvious. Red, we don't know. C, we don't know, the constant. And we don't know a. Now, is this a linear function? Linear means that you have like constant coefficient multiplying your variables. But now your variable a is in the exponent. And then it's multiplied by c. So like two variables, one of them is taken to the exponent and one multiplied. Doesn't sound like so linear to me. And if you don't know if it's linear or not, you try. Homogeneity, superposition. Okay? And then you figure out whether it's linear. So who thinks it's linear after all my descriptions? Who thinks it's not linear? Non-linear? Who doesn't know? No? Okay. It's non-linear. Like you can try, and it just becomes non-linear. Okay, so now the question is, okay, so the answer is no. But, can we still do this fit? Is there an operation that we can actually transform this problem into a new problem that's actually solvable? What did you say? You said to take a log? Great idea. 12 points. 12 points. Take a log. Now, what does log does? You know, when you take a log of something, log of a product is the log of the sums. It's the sum of the logs. Okay? That's a nice property of logs. And log of an exponential is that whatever is in the exponent becomes a coefficient. Okay? So it comes out of that exponent. So that could actually fit here. And that's an interesting proposal. So it can be made linear. And so we're going to create a new model, take the data, and compute the log of the data. If we compute the log of the data, the new model is log of y equals log of c plus a times x. Why? Because when you take a log of c e to the ax, it's actually log of c plus a times x. And when I say log, I mean ln, the natural log. Okay? That's what I mean. Although it wouldn't have mattered because it will just again be another just constant multiplying, and that constant would be absorbed in c and would it be absorbed in a somehow. So it's not going to be a problem anyway. So just taking any log would be fine, and you just need to then deal with the constants. Okay? Does that make sense? Now, it's not the same problem. It's not the same problem, but it's a problem that we know how to solve. Do you know how to solve it? Oh wait, c is still within log. Ooh. So that's not a constant coefficient or something, is it? Or is it? Instead of log c, can we just call log c a b? Can we call log c a b? Okay, let's do that. So if we call log c a b, then the problem looks like b plus a plus ax. Right? That's the problem. So now we have x's, we have y's, but we can take the log of the y's and then get log y. So now we have a and x's and some y tilde, or some other new y's that are really the log of what the data we measured. And we can probably solve for a regression, a linear regression that solves for B and A. After we solve for B and A, I can then compute what C is from B by taking e to the power of B. And that would give me log of C. Is that right? Yeah. Okay? All right. So if I take actually the log of y, then the data kind of looks like that. Does it look linear? Kind of. Yeah, a little bit oscillatory, but quite linear. So that means that this is indeed very close to being exponential. Okay, so when I take the log, then it becomes kind of a linear response to the time, which is great. That means that now I can fit and perform regression. So the knowns are x1 and log y1, x2 and log y2, x of n log yn. Right? These are the knowns. And the unknowns are a and b, some parameters that are missing that we don't know. And now we want to put that into a matrix a times p equals log y and see what happens. Okay? So, did I put a y here? I'm just going to put a y tilde, but really I mean y tilde equals log of y. Okay? All right. So what is A? The matrix A. Well, I want like this and like that. So my unknowns are A and B. These are the unknowns. And the first equation I have is for x1 and log y1. And I've got this model. A is multiplied by x. So I need to fill in here. What do I need to fill? x1. And then plus b. That means that the second column needs to be 1. So the first equation that I have is x1, like this, like that. x1 times a plus b. Okay, that's the first equation. Equals to log y1. That's the first equation. Second equation, well, I've got x2 and log y2. So again, like this, like that, and I would get x2, 1, and then log y2. And then I can keep going with all my data. And I would get a matrix A, which is made out of these x1, x2, x3, all the way down. And then the second column is 1. And then here are the logs of y1, y2, y3, y4, y5. Okay? So now I got it in a form that I know how to solve. How do I solve it? Atta, minus 1. Atta, yeah, tilde. Okay? So now I know how to solve it because matrix A is given by the data. Vector Y is given by the data. These are known. And then I can solve for A and B by solving the least squares. Okay, so I do a linear fit, which is great. I got this nice equation. And in order to actually compute the optimal C, I need to take e to the power of b hat. Whatever I solve for a b, I need to take e to the power of that to really get my C coefficient. Because again, this is log C. I said B equals log C. So now in order to compute from B what C is, I need to do e to the power of b hat. Does that make sense? Yeah. Can you? Why did we put C and B in hat? Because we don't know actually what is the A and B. We have some optimal one that is the hat. You know, that's or the star, I guess. I guess it should have been star. These are the optimal. That's the optimal. Okay. And here also, it's not p hat, it's p star. Sorry. Apologize for that, but thanks. This is the optimal p that we got from least squares. From that, we got the optimal a and b. And from b, we can get c. Okay? It's great. Oh. So now here's a super interesting problem. You see those points? I generated them. You know how I generated them? I created an array that is 0.1 times x plus 1. And then I just picked 100. Is that 100 there? There's 100 points? There's no 100 points there. Don't look at the x-axis. You know, it's just like it's a little bit misleading here. There's a fewer points. So just ignore that part. I don't know why it's that, but anyway. I picked, no, actually, no, that's fine. That's actually fine. That's fine. I just didn't enumerate all the x's. I enumerated x's every 5. Okay, so for x equal 5, I've got for x equal 0, I got a point. For x equal 5, I got a point. For x equal 10, I got a point, and so on and so forth. So this is actually how I generated. But then I picked up just random values, and I perturbed y to be slightly different. So I added noise, okay, to my measurement. So I generated an array that looked like that, according to this model, and then I added noise. I added some other value, ni, so I guess n. I added some noise. And so plus noise. And because it's noisy, then you got, it doesn't look like necessarily exactly on a line. Okay? Because it's noisy. Added noise. My algorithm gave me, for value x10, I should get, let's say, 0.1 times 10 is 1, plus 1, that's 2. And instead of having it 2 exactly, I got a little bit below 2, this point. It was just a little bit below 2. And for 20, let's say 0.1 times 20 is 2, plus 1 is 3, and I got a little bit over. This one is a little bit over 3 because of the noise. Does that make sense? Now I'm going to leave you, folks. I'm going to move to the center. Thank you. I'm just going to now look at those fine faces. Okay. So the question is, what is the question? Huh? I look at those points. I don't know how they were generated. I don't know. I got these points. I'm telling you, as an oracle, how I generated them, but you actually don't know how I just gave you those points. Okay? So you're given those points, and you're going well, they come from a certain model. You just don't know what the model is. So what can you do? Try to fit a model. And what model, for example, you could fit on? Which model would you fit for these kind of points? Linear model. Why not? Maybe it's linear. And you go okay, here's our model. Y should be equal to ax plus b. And that's actually the true model that was generated, how the points were generated by this true model. That's actually physically how those points were generated from this model plus perturbations. And we want to find what is this a and b from the data. Now, the real a and b, a should be 0.1. The real b should be 1. But we just have these points. We want to figure out if we can fit and extract those values, right, from this noisy measurements. And so I have this model, and that means that I'm going to try to fit a line. And I use the least squares, because I showed you and we talked about how to do least squares from those points to fit a line. And indeed, of course, this is the line I got. Kind of looks reasonable. Does it look like a reasonable line? Yeah, it looks, yeah, I would draw that line. And then I got these values for P. These values make sense? They're close. Oh my God, they're really close. It's like 0.1015. That's pretty close to 0.1. And this is 0.9757. That's pretty close to 1. So I got actually pretty good numbers. I can't get it perfectly because it's noisy. I mean, I got the closest one, but you know, it's not perfect. But I got really close, which is good. Okay? So the error, what I minimize is this vector E. That's the error vector between this. And E has a value. What is E? What is E? E is this A times X minus Y, and then the norm of that. Okay, that's the vector E. So I created the matrix A, I created the vector Y, I did the fit, and that was the error, and that's the norm of the error. The norm of the error is 3.85. Okay. Fantastic. Yeah. Yeah, for this particular P, A times P minus Y, the norm of that, should be equal to 3.85. Okay? So the error vector is actually the A times P, the one that we, P star, the one that we actually solve for, A times P star minus Y. That's the error vector. That's how misfit, you know, that's the best. And actually it's small, it's the smallest possible because that's what we find through orthogonal projection. It's the smallest. There is no smaller in this norm 2 sense. It's just, there isn't. Because we proved that this is the closest. So that's what we got, 3.85. Now the question is, you kind of look at the data, but is it actually linear? Maybe we can fit some other polynomial, maybe a second or third order polynomial to this. Would we get a smaller error? What do you think? Let's try. Let's find a new model. Say, oh, this data, somebody says here, no, this data is not linear. This data comes from a third order polynomial. And you go like, no, this comes from linear. And you go like, no, it's third order. It's like, let's see. Let's see which one is better. So the other person says, oh no, the model is ax to the power 3 plus bx squared plus cx plus d. That's the right model. And this is the result. And to prove that was right, the error is now 3.71. Before, it was 3.85. Now the error, the norm of the error, is actually 3.71. It's lower. This actually fits better. Look, it actually, you know, kind of like, you know, kind of wiggles nicely around those points. Ah, it's closer. So maybe that's better. Maybe that's better. Any comment? Yeah. Well, what does even overfitting means? That's right. But we don't know right now what the model is, right? Like we have just data. Somebody says, oh, it's like a linear. That was third order. Third order wins because the error is smaller. Okay? Any other suggestions? oh, let's do 10. You said 19, but the 19 is a lot, so let's just pick 10. What about 10th order? Let's pick 10th order. 10th order polynomial, I think it's, no, 8. Or some order. Here's another order. This is an 8, this is 7th order polynomial. Whoa, that wiggles even nicer within those points. Kind of go within those points. And our error is even smaller than that. That is then the right model, right? Because it fits the data better. Or is it? The problem is that what we're doing when we're increasing our model order, we're able to then start fitting the noise. Remember, the data was generated from a linear source. Then noise was added. Now, instead of fitting the actual data, we're actually trying to fit the noise. And that's why the error is reduced, because we can actually make the error 0. How? Pick a curve that will go through all the points. That's a great function. 0 error. Is that the right one? No. So this is what's called overfitting. We're just overfitting to the data, but we're actually not resolving the actual model that generates the data. So it'd be really terrible to predict points in between if we generate new ones. It will be really terrible to generate, to predict outside of that range, because it'll just be completely different, right? So the problem that we're seeing here, that there's actually overfitting sometimes. So we have to really know how to pick the right model. If you don't know how to pick the right model, we're kind of, I want to say, but it's a problem. Okay. So the question is now is, how do we do what we called a model order selection? How do we select the right order for our data? That's a real problem when we try to deal with data in general. When you try to do classification, when you try to do detection, machine learning, fitting curve regression, anything, sometimes we may overfit. And then we actually don't estimate the right parameters of what is actually happening, so we'll have a hard time predicting or figure out points that we didn't measure. So our model will be kind of, in some way, useless. And it happens all the time. So the question now is, okay, well, it's a new problem. So now at least we understand what is overfitting, because I can fit anything that would reduce the error to 0. But obviously, our model is simple. So we like to keep it simple, keep it real. Yeah. Interesting. The suggestion here was, can we keep some of the data to train some other thing? Yeah, we'll get to that. Give me a second. And the question is here is, what is the right model for this case? I know I didn't tell you how I generated it. Okay? What do you think? Is it linear? Let's do it. Let's put a line. Yeah, line kind of fits. Some points more than others. I've seen papers showing this linear fit in the graph and saying, oh yeah. Okay. Anything else? I think it will predict quite, it's okay, I guess. Anything else? You want to increase the order? Let's go for second order. That's second order. Ooh, wow, that looks better. Right? Yeah. Oh, wow, quadratic. You can kind of see what's going on. What about 10th order? 10th order? It's 10th order. Wow, even nicer, but something's kind of like awkward from the sides. Right? So what I'm going to do now is I'm going to plot the error versus the polynomial order. Right? We can try all these orders and then see kind of what's going on. This is what's going on. So 1 has an error of a 30 something, whatever that number means. I don't know what it means, but it's like sounds large. And then when I go to second order, now it's like below 10. Third order, it's a little bit better, but not much. Fourth, fifth, you know? So you think of nature, she likes to have things simple. So you can think of like, well, what is my simplest model that actually fits the data? And if I actually stare at this, I would say, you know what, there's a big jump from 1 to 2, but there's a very small jump after that. So this is called an L-curve method, because it kind of looks like an L. You see that it looks like an L? And so if you see kind of a sharp kink, you go like, well, after that, it's probably just overfitting. Okay, so you could do it that way. That's one way. So that's one method to find the order selection. Now the problem is that sometimes your curve is actually more something like that. And so it's not as distinct, you know? Yeah. Yeah, you can add the other functions, and then depending if you parameterize it through a certain model. So this is a polynomial, for example, and the order of the polynomial. But you can have some other functions that have more coefficients, right? Because it's all about the number of coefficients, really, right? Because second order polynomial will have more coefficient than a first order polynomial, right? That's by the order I mean, like how many coefficients you're solving for. So the L-curve method is useful, but not always, because it's not always distinct. Okay, so then we have this data, and what you suggest is like, well, if we fit all the data that we have, then we obviously start fitting the noise. And we're always going to improve our error. But let's separate our data into two sets. One that we would use to fit, and then one that we will use to test. Because if our model is right, then if we have a good fit, then on the test data, it would fit pretty well as well. But if our model is not right and we're starting to fit noise, then we'll have large deviation. We won't be able to predict kind of what's in between of the data that we actually didn't use in the fit. Does that make sense? So we separate our data. We have all these like blue and red points here. So we separated it into a training set and a test set. Okay? One training, one test. And then we fit the model onto the training set. And we evaluate then the error. Instead of on the training set, we evaluate the error on the test set. Because it should fit it if it's part of the model. If not, then it isn't. Of course, we're going to fit well the training set because that's what we're trying to do. But the test set, the fit didn't even see it. Okay? So we evaluate the error on the test set. Okay, so now the issue here is, first of all, I have less points. So my estimate of my parameter may be a little bit off more, right? There's always a trade-off there. So, but as long as I have enough data, then that should be okay. But if I'm limited with a lot of data, then that could be a problem. Because of deviation, maybe my fit's not going to be great anyway, right? So that's one thing. But here's the training error. And the training error is always decreasing. Why is it always decreasing? Because we could always fit the noise as we increase the order. So always, we can reduce it down to 0 eventually. Down to 0, we can reduce it if the order is, large enough. Now I'm going to plot, though, the error vector evaluated on the test set. the one that the fit didn't see. Now let's see what happens. That's what happens. So the error on the test set for a model order of 1 was pretty high, similarly to the training set. When we got to 2, this was reduced, but also this one was reduced considerably. So that means, oh yeah, that's an improvement, and so perhaps I should consider a model order of polynomial 2 to be the right one. What happens after that? Well, 3 decreases, 4 decreases in the training set. But what happens in a test set? Well, 2 and 3 seems to be similar, right? 2 and 3 seems to be similar. It happens just because we don't have enough data. If we had more and more data, probably 3 would have been a little bit higher, because the data actually was generated from model order of 2. But then after that, it increases. So you can say, this is test set, this is training set, this is test set, and I'm going to pick either 2 or 3, right? And probably if 3 doesn't really add a lot much, then I should just pick 2. Okay, as the right mode. Yeah.
So when you're having the training and test data,
Yeah, that's where statistics comes into play, and that's where CS70, EECS16, 126, probability, random. Yeah, plays in a role to understand actually how that is going to impact your variance of your estimate. How to divide, you can also take 189 and what's the other one? I forget. 188. Okay, these are good classes to understand how to deal with that. There's a lot of practical issues with separating those. Sometimes you just don't have enough data to even do the fit, right? So then you'd pick a smaller, a large training set with a smaller testing set. But ideally, it will be 50-50. But sometimes it's impossible. And how do you pick them? Do you pick them sequentially? Do you pick them in random? You know, there's all these questions, right, that you can ask. So, okay, well that's pretty cool, right? So this is called cross-validation. You basically cross-validate within your data that you actually get. And you can do many trials. You can pick another random set, do a new fit, and then compare. And then by that, you can eventually pick up the best model order selection, okay, in order to be able to get the right order. Cool. It's useful, right? Extremely useful. Can you imagine yourself using it? I totally imagine myself using it. Okay. Let's talk about outliers. I mean, outliers are everywhere, right? It could be, some error, like, weird error that happens. I don't know, like you measure something and then some cosmic ray hits your whatever processor and flips a bit. Could be that. Could be a glitch. It could be, like you've got like a, group of students and they do kind of an average pretty well according to a Gaussian distribution, but then there's this, person that never makes mistakes, and there's another person that makes all the mistakes possible, and those would be outside of that distribution, right? That happens. So outliers are extremely prominent. And the question is, let's say you have now some data that was generated, in this particular case from a linear model, but then we got like this measure number 1, 2, 3, 4. Measure number 5 was a fluke. It's kind of like, I'm trying to measure something, and then kind of like my daughter is going like, Dad, and then it's like I'm trying to measure number 5. She goes, Dad, and it's just, measure went away, and I get this number, and now it's recorded, and keep going, right? So we got this outlier. Now this one's obvious that it's an outlier, but like sometimes it's less obvious. And the question is, what does these outliers do, and how do we deal with them, for example? Okay. So, what if I try to fit a linear model to this thing? What is this linear model in least squares, right? Linear model, least squares. What we'll try to do, we'll try to minimize the norm of the error, or the sum of the squares of those kind of distances between the points and the line that I have just fit. That's what we'll try to do. So we'll try to minimize that, right? But I've got this like point that's really, really far away. And because this point is so far away, when I actually do the fit, in order to minimize the error, right, the norm of the error, it will have to actually pull my line. Oh, I got stuck. I said pull the line, and then this line was pulled. It's pretty, I'm just going to talk to you now. Stop it. So it will pull the line towards minimizing, try to reduce this error. This error is so large, right? And it's the sum of the square. So like if you have something that's really far, then it's like really important that we get really close to it. Otherwise, our penalty is squared in terms of, instead of error. Ooh, so I'll pull my line a little bit upwards. And that is a problem. Why? Because now I've got a huge error in my estimate. So I'm sensitive to outliers when I do least squares. Least squares is sensitive to outliers. That's kind of my point. If I okay, so what can we do? You want to discard the outlier. How do you discard the outlier? How do we discard the error? Well, what we can do, we can compute the error vector, right? And the error vector will consist of small number, small number, small number, small number, huge number. Small number, 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 small number. But one huge number. And then you're going to say, oh, my E vector is like 0.01, 0.01, 0.02, that's the E vector, and then suddenly 10. And then how do you remove outlier? You would put a threshold, maybe you want to say. Threshold, you want to say. You put a threshold. How do you pick the threshold? If you pick it too low, you're throwing away some data. If you pick it too high, you're going to miss the outliers. So how do you pick it? You need to know a little bit probability and statistics. So take CS70, 126, and all the stuff that has to do with random number and stochastic processes, because that would allow you to pick optimally from a statistical point of view. But for this class, we go like, oh, if the error is above a certain threshold, we throw it away. And if we throw it away, and now we fit without that, then you see how nicely that line fits? It moved back. So now the blue line is the one, is it blue? I can't even see what it is. Black, blue. What color is that? What color is that? Black? Okay. The black line is much fitting to the data now better, right? So we did what's called an outlier rejection. Another thing is, one of the issues that we dealt with was, well, because the norm that we use is the 2 norm, it's a Euclidean norm, in terms of distances, maybe we can find actually a new norm that is less sensitive to those large distances. So large distances don't get that much penalty. So you can think of a weighted norm. You can think of maybe, it turns out actually that the 1 norm, this Manhattan distance that I was talking about, actually is less sensitive to outliers. Okay, so there's other ways to deal with that. You can also solve it iteratively, and in this particular case, we put a penalty of 0 of that error, because we removed it from the fit. But we can be a little bit more forgiving, say, oh, you know what? Anything that's really, really far, how about we scale it down in terms of its weight by, let's say, 0.1. So that comes down to like an inner product that is weighted. Remember the weighted inner product? So that would be a weighted norm associated with that weighted inner product. So there's a lot of tricks that we can do in order to be robust to outliers. Oh, let's go back to multilateration. We kind of covered this, but it's just my other person from like a semester ago taught you that over the interweb. Because have you seen this lecture about the multilateration? Raise your hand if you've seen it. Okay. In that case, if you remember, we got GPS. We have satellites that are at different positions, and we measure the distances to those satellites. Okay? And we came up with, and we don't even know time, so we have to also solve for time. So we came up with those nice equations that if I know A1, A2, A3, 4, 5, and I know and I do cross correlations and stuff to figure those out, but also I got the different timings. So now I've got the different timing of arrivals between the signals from each satellites. I don't know the absolute reference, but I know just the delta. Then I can actually solve a linear set of equations that we'll be able to then to figure out the x position as well as the time. And that's what we did. And that's what we're going to do in APS Lab. But when you have a lot of satellites, then you actually have more equations than unknown. The unknown here are x1, x2, and tau, the time, I guess. But then I might have more equations than unknown. And we said, oh, we can solve it with least squares. And least squares will always give us a good solution. Right? Right? We also said that A transpose A needs to be invertible. If it's invertible, then we can invert it. But if it's not invertible, that's going to be a problem. And we said, oh, wait, but if I know that if I know this, how do I know it before computing A transpose A? How do I know it? Well, if I look at A and say, well, A is full rank, then there is a solution. Okay? So that's what I said. Okay? So now we're going to prove that it is really necessary to know that A is full rank in order to show that A transpose A is invertible. A transpose is a different matrix. It's a square matrix. A is actually a long matrix. Okay? Tall. Before that, if you remember matrix transposes, I want to just show you this rule here. If I have AB and I transpose that matrix A times B, this kind of looks, this is A and this is B. You see the red and the red, the blue here and then the blue here. Then A times B would be kind of like it's a combination. It's going to be super red on this diagonal and super blue on this diagonal over here. Like this, like that, like this, like that, this, like that, this, like that. And so you got this kind of I'm just showing it as a gradient. So you take this and you transpose, then it's going to look like that. The gradient is going to look in this direction, right? Now I'm saying that AB, if you multiply A times B and then you take the transpose, is the same thing as first computing the transpose of B, computing the transpose of A, and then multiplying it together. So in this case, B transpose looked like this, A transpose looked like that, and then you can actually see that the results of those gradients look the same. I'm not going to prove it. You can actually do the calculation by yourself. And pretty much this equation is true. If you have AB and then transpose on that, it's the same as B transpose. You flip them and then transpose them. Okay? You can do it in your head. You can do it in any method you like. But this, you have to believe me that's true. But you can do this. It's pretty easy to show. And I try to show it with this color scheme. Okay, so AB transpose is B transpose times A transpose. Okay. So let's look about the invertibility of, I'm looking at you. Invertibility of A transpose A. Remember, invertible means that it's a trivial null space. It means that linear independent columns and rows. It means a lot of things. Eigenvalue is not equal 0. The determinant is not 0. Lots of stuff it means. And here's the theorem. Well, the matrix, well, it's not the theorem, but like the matrix A transpose A, this is the statement, is invertible oh yeah, okay. Okay, do you agree with me that the A transpose A is invertible if and only if the null space of A transpose A equals 0? Like basically there's just a trivial null space? Do you agree with me? That we proved, right? Already. Okay, that's true. Here's the theorem. That's what's got me confused. The theorem says that the null space of A transpose A is the same as the null space of A. Okay? The null space of A transpose A is the same as null space of A. So that means also that if the null space of A transpose A is the trivial null space, also the null space of A is the same, and vice versa. And therefore, A transpose A would be invertible if the null space of A is 0. Okay, so how do we prove this? I'm going to show you pretty much that this is true. And what we're going to do is we're going to show two ways. One, we're going to show that if we have some W that is within the null space of A, then this W is also within the null space of A transpose A. Okay? That means, well, it just means that W is in the null space of A transpose A. But it doesn't mean the opposite. So we also need to show the opposite, where if we have a V that is in the null space of A transpose A, then V is also in the null space of A. So it's just both ways. And if we show both ways, that also means that the entire null space of A and A transpose A are the same. Okay? That's what it means. If we show both directions. So how do we prove? The first one is actually quite easy. Okay? We say, battery's almost done. We say W is in the null space of A. That's the thing we know. Okay? That means that, what does it mean to be in the null space of A? Is what is A times W? If W is in the null space of A, A times W is 0, right? Yeah, that's easy. Okay. What about A transpose A times W? Can I multiply from the left by A transpose? I can. I'm going to multiply from the left by A transpose. That means that A transpose A times W equals to A transpose times 0. What does it mean now on W with respect to A transpose A? What does it mean W in terms, what is A transpose times 0? 0. So what does it mean if I have now A transpose A times W equals 0? W is within the null space of A transpose A. So even though it's in the null space of A that we know, we can show that is also within the null space of A transpose A. That's easy. So A transpose A equals W, times W equals 0. And that also means that check, we know that if W is in the null space of A, it's also within the null space of A transpose A. Now we need to show the opposite. The opposite is a little bit more tricky, because there we know that V is in the null space of A transpose A. That means that A transpose A times V equals 0, right? That's what it means. But we need to show that A times V equals 0 by leveraging A transpose A times V equals 0. Now that's a problem, because I cannot, like, how do I go back to A times V and show that equals 0? I know that A transpose A equals times V equals 0. Just going to from A, like, how do I show AV? Yeah. What is inverse of transpose? Transpose. Sorry, A is a long matrix. What is an inverse? There's no inverse of that. There's an inverse maybe for A transpose A, but there's no inverse. So it's, how do I go back to just being like A times that equals 0, right? That's, yeah. Can you multiply by both sides by A? How? Well, let's try that. That's an interesting suggestion. We multiply by A. A transpose. That is actually now a fat matrix, right? It's like what's that going to help me? How do I do that? You know, you see what the problem is? I really just need to get to this point though. So I need to kind of eliminate stuff.
Multiply both sides by A again, and then multiply both sides by the inverse of A transpose A.
But we don't know if it's invertible. I don't know. What do you say? What do you mean orthogonal vectors?
If you multiply like a 0 vector by another vector, it's still 0, right?
From A transpose A, V equals 0, I need to get to AV equals 0. That's a tough one. There's a beautiful trick for that. Okay? Yeah. Using inner products. Maybe. Maybe you're getting to somewhere. Let me ask you this. When is AV equal 0? When V is in the null space of A, right? But AV is a vector, right?
Yeah.
What if I look at the length of that vector? If that length of that vector is 0, does it also mean that it's actually 0? Okay, A times V, if the length of A times V is 0, does it mean that A times V equals 0? Does that? Again, A times V, I look at the length of it. What is the length? It's norm. If the norm of that is 0, does that also mean that A times V equals 0? Have to, right? That's one of the criteria that we actually had in the beginning. We said, oh, the norm, if A times V equals 0, then A times V has to be 0, all the elements. Otherwise, norm is always positive definite, right? That's the definition of a norm. It's positive definite. It cannot be negative, right? So if you sum the square of all the elements and they reach 0, then that means that the elements are 0. Okay? Now, why am I going for a norm? Because a norm, what is the norm of AV? The norm of AV is the square root of AV transpose times AV, right? That's by definition. What is the norm? X. What's the norm of X? X transpose times X, right? Square root of that. That's the norm. Okay? So we need to show that AV equals 0, but that also means that enough for me to show that the norm of AV equals 0. Okay? I can now manipulate that somehow. I can also say, oh wait, if the norm of AV equals 0, is the norm of AV square also 0? What is the norm of AV square? Well, the norm of AV square is AV transpose times AV. That's the norm of AV square, by definition. And again, if you don't remember, then if I have a vector x, the norm of x squared, that equals to x transpose times x. So now translate that. Instead of x, put it AV, and then you get AV transpose. Now remember what I told you about what is AV transpose? I can open those and say that is also V transpose A transpose times AV, right? Because then you flip the direction and you transpose both of them. That's how you open a transpose parentheses. Oh, now I'm getting somewhere, right? Now I'm getting somewhere. Because now I started with AV, the norm of that squared, and now I'm getting to something that is A transpose times A. Now what do I know about A transpose times A times V? I need to kind of like just erase something and then start again, just so you to show it. Okay. That's pretty cool, right? Okay, so I opened it, and now I get this. But I can open that too. Like this doesn't matter. Now the order doesn't matter of multiplication. So effectively, this is V transpose A transpose A times V. But what is A transpose A times V? What is it? 0. So now this is equal 0. So I started by knowing that. I looked at the norm of AV. The norm of AV turns out to be 0. Hence, AV is also 0. Does that make sense? Yeah. This? Yeah. This is what I showed you like 2 slides ago. If you have A times B and then transpose that, is B transpose times A transpose. Right? That's the reason I showed that one. So when you have parentheses and then transpose, then you flip the order and then you transpose each one of those elements. Okay? Okay, so that's how we got there. And that is a very useful trick. Every time that you go from A transpose A, you want to go back to A times something, then you use the norm in order to show stuff there. That's kind of one of the skills of kind of knowledge. Like, oh, where does A transpose A appear? Well, it appears in norms, so maybe I can leverage that. Okay? Check. Back to GPS. And now I have like 1% of battery and 5 minutes to go, so I think we're good. If it shuts off, we finish the class. Or if somebody can give me a charger. Well, let's give me a charger. I'm like freaking out here. Okay, so let's go back to GPS. Does it ever happen that within GPS we may have a problem? Oh, thank you. Yeah, it's iPad. Thank you. Thank you. Okay, so now we have the GPS case, and we have like, this is our position, here are the satellites. And let's say the satellites are at 0, 0, 2, 1, 4, 2, 6, 3. Okay, let's say the satellites are along this line. And what we do is we measure our distances. And so now we know, we measure those distances. And now here are their equations. We have 3 linear equations from 4 satellites because we eliminated the quadratic one, because of the quadratic, if you remember. We had 4 nonlinear equations. Now we have 3 linear ones, and those are these. And now we can go and fill them up in the matrix. Let's choose the first one. The first one is 2 times A2 minus A1 transpose times X. So what is A2 minus A1? Actually, what's our unknown? Unknowns are X1, X2, and then there's no time here, so just X1 and X2. Okay? All right, we just eliminate, like we assume that we know the time. Okay, so X1 and X2, that's great. Now we need to multiply A2 minus A1 with our X's. So what is A2 minus A1? Let's see, it's 2 minus 0 and 1 minus 0. So it's 2 and 1, but it's times 2. So it'll be 4 and 2. So like this, like that, equals to this, whatever it is. Okay? All right? So effectively, I got 4 and 2 times x1, and this are all known, because I know the distance, I know what A is, I know the position, I know everything. And then my second equation, if you actually do, it's A3 minus A1 times 2, it's 8 and 4. My other equation is A4 minus A1 times 2, that's 12 and 6. And now we want to solve for x1 and x2. Great. Take a look at this. When is it invertible? It's invertible when this matrix is full rank. What does it mean full rank? That its columns, for example, are independent. Are the columns independent? They aren't. They're not independent. They kind of look just a half. This is a half of this, right? Okay, well, let's still try it. So A transpose A, like this, like that, like this, like that. You get 224, 112, 112, 56. What happened? Is A transpose A linearly independent? No. Is it invertible? No. No solution. Well, infinite solutions. Yeah, there is a solution. It's just infinite. Right? Because now I have A times X equals Y, but now I have infinite solutions. What? What's the geometry here? So here's like this is why we came to this space. This case, if you look at the satellites, they were along a line. That turns out to be a pretty bad choice. Well, situation. Because if you look at this distance over here, this is the quadratic equation. You know, that's where I'm supposed to be, right? And based on my distance here, this is the intersection, right? What happens with this one? I should also put like a big circle, right? That is centered around that. Turns out that circle actually intersects exactly the same points because it's along a line. And then this one also intersects. And so now you've got like 2 points where you could actually be. And when you do the linear, then you basically have a line that your solution could be on, and that's why it's infinite solution in the linear case, in the linearized case. So there's an ambiguity here. Whenever there's ambiguity, when you try to linearize, it becomes like